Hi, Trenton. Um, I I'm not sure that I totally understand your question when you say just to go over logs. So I will give a brief introduction to logs and why they're useful for the specific problem you sent me, and then I'll talk through how you can get started on that problem that you asked about. So let me get this going here. Okay, so if you go back to first principles, just the definition of a log. This is what a log equation means. This is how it's defined. Log base A of something equals something else. So log base A of x equals y is the same thing as saying that this number A raised to the power y is x. So that's just how logs are defined. So just for example, somebody could ask you, is log base 3 of 2 equal to 9? Is that true? And to check that, all you do is you take 3 to the ninth and ask yourself if you get 2 or not. So you just ask yourself this question. So of course 3 to the ninth is humongous, 3 to the ninth is not 2, so the answer is no here. But on the other hand, if somebody asks you, is log base 3 of 9 equal to 2, you just do the same thing, just take the base here, 3, to the second power, does that equal 9? And of course the answer is yes. 3 to the second does equal 9. So it is correct to say that log base 3 of 9 equals 2. Okay, so that's just what logs are. Why do we care about them? Why are they useful? Well, there are many reasons, but for the sake of your particular question, this property of logs right here is what's useful. So let's just say in English what this is saying. It's saying log base A of x to the r equals r times log base A of x. So what it does is it turns an exponent into just into multiplication, if you like. It turns exponentiation into multiplication. And so another way you can read that is equations like this are true. Log base A of something, of stuff, to the t power. You can move that t power outside, and now the t is just multiplied instead of being inside an exponent. So having a variable in an exponent can be inconvenient. So a log allows you to take that variable out of the exponent and put it down. And if your variable happens to be an x, this equation is also true. Log base A of whatever, as long as that whatever is raised to the x, you can take that x down. And now x is multiplied and it's not an exponent. So the way that this property arises is when you see equations like this. Somebody asks you, okay, solve 3 equals 7 to the x for x. And so before I solve that, I just want to do another motivational example that may or may not have anything to do with what we're doing. But consider an equation like this. Square root of x minus 1 equals 7. So if you think about what's stopping you from solving this equation, well, you want to get the variable isolated, right? That's how you solve any equation if you can. So what's stopping you from getting this x isolated? Well, if that square root weren't there, you could just add 1 to both sides and be done with it, right? So having an x inside of a square root is an obstacle to isolating the variable. But that's okay. You can just square both sides. You have to square both sides, right? So there's a 49 over here. And now you could add 1 to both sides, and you learn that x is 50. Okay, so that's the idea of an example like this. Having an x inside of a square root is an obstacle, so you can get rid of the square root. So the same principle applies here. That x is in an exponent, and that's an obstacle for you. That's inconvenient. That's currently stopping you from isolating x. So what do? Let's just take a log of both sides. You can take any log you feel like of both sides. So you can take log base 10, you can take log base 3, you can do whatever. I always do natural log because that's the button I find easiest on my calculator. But in any case, you could also do log base 10 because the log button is on your calculator. So I take natural log of both sides. That's exactly analogous to squaring both sides like we did in the previous example. Taking natural logs of both sides, what does that do? Well, first let me just evaluate natural log of 3. That's just a matter of entering it into your calculator. On the right-hand side, though, remember what logs do to exponents. They allow you to bring the exponent down, and it used to be an exponent, now it's not. So the equation you started with, where the x was in an exponent, you now have an equation where the x is not in an exponent. And that's nice, because now you just ask your calculator, what's natural log of 7? My calculator gave me 1.94, etc. And so this equation here now, the numbers aren't nice, but it's something you can solve, right? It's just a number equals a number times x. So you can just divide that 1.94591 over, and that's what I get. X is approximately 0.5646. Okay, so that's how we're using logs in this particular chunk of material. They let you solve equations like this, where your variable is in an exponent. Okay, so after all that, let's now consider the exact problem you asked about. So G of T here models consumer debt. T is years since 1980, and G is measured in trillions. So when they want you to find the year in which consumer debt is 2 trillion, they're asking you to solve this equation. So you want to know when, so you don't know T, does G reach 2? And so you want to find T. T is what you don't know, but T is inside an exponent. And logs are exactly what allow you to move a variable down from an exponent. And so let me pause right here, and let me just remind you of our log formula. It says log of stuff to the t equals t times log of stuff. So if you want to use this property, all the stuff inside the log must be raised to the t power. And so a common error when solving an equation like this is to start by taking log of both sides. Okay, you don't want to do that because this 0.365, etc. is not raised to the t power. Okay, so if it were, then I guess you could go ahead and take log of both sides. But if you want to use this property immediately, you need everything you take a log of to be raised to the t power. So what we're going to do is just, well, essentially all I'm saying is I want this 1.0845 to the t. I want that by itself. Because if this is by itself, then everything is raised to the t power. So the first thing I'll do is just divide that 0.3651 over. And my calculator tells me that 2 divided by 0.365, etc. is 5.4776. Okay, so you want to make sure you do this. If you don't want to start by taking log of both sides. You want to divide this coefficient over first because it's not raised to the t power. So this is the equation I end up with here. The numbers look nasty, but it's really no different from that equation we just solved a second ago. You have number equals number to the t power. You don't like having that t in an exponent. That is stopping you from isolating the t. So I took log of both sides, and when you do that, the t comes down. And so now it's just a simple matter of asking your calculator what these numbers are. This number here and this number here, and dividing over. Okay, so I hope that answered whatever questions you have. Of course, you can always email me if there's anything else.